All right, let's talk about combustion. So this was mentioned in the previous lecture, but combustions are pretty much the reactions between hydrocarbons, molecules that contain carbon and hydrogen at the very least. They might even contain oxygen within their formula, but they have to have carbon and hydrogen, and they're known as hydrocarbons. The reaction between a hydrocarbon and oxygen gas, which is diatomic, so O2, yields carbon dioxide and water. This is the premise for a combustion reaction. You need to remember that you will form carbon dioxide and you will form water when a hydrocarbon reacts with oxygen. And with that premise, now we can actually go and balance the equations. Now I'm going to show you an algebraic way of going about solving it. You need not do this necessarily, but I'll show it to you just in case you want some extra options. Notice that for both equations, the amount of carbon is in the form of x. So to balance the carbon, and that will be the first thing you want to do in a combustion reaction, to balance the carbon, you want to place an x in front of your carbons, right? That will make sure that you have the proper number of carbons on both sides. Now for hydrogen, you have y amount of hydrogen, but on the product, you already have two hydrogens. So to ensure that you end up with only y amount of hydrogen, you will first have to divide the water by 2 and then multiply it by y. So in other words, you will balance the water by multiplying by y over 2. And what we basically did right here is we balanced first for carbon, now we balance for hydrogen. And the reason I did that and I left the oxygen until the end is because oxygen is present in 1, 2, 3 different molecules. So it's present in more than one molecule per side. So you want to leave that till the very end. All right, now that we have the proper number of carbons and the proper number of hydrogens on both sides, now we look at how many oxygens we have collectively on the right side of the equations. And you simply multiply the subscript by the balancing coefficient. So for CO2, we have 2 times x. For water, we have 1 times y over 2. And that's what you have in terms of oxygen on the right side of the equation. So you have 2x plus 1 times y over 2, or just y over 2. That's true for both equations. But now you have to keep in mind that you haven't yet balanced the O2. So I'm putting this additional variable in front of O2 to balance it. And I'm doing the same thing down here. They're different because the second molecule here contains oxygen within the formula. So what you do is you say, okay, we know that on the right side we're going to have 2x plus y over 2 amount of oxygens. On the left side for the first equation, we have to have 2 times z. That's all the oxygen that we have on the left side. But over here we have z, which was part of the original compound, in addition to 2 times n. So z plus 2n better equal 2x plus y over 2. And up here, 2z better equal 2x plus y over 2. This is the symbolic way of balancing the equation. And of course, to find the value of z, you will have to divide everything by 2. To find the value of n here, you will have to subtract z from both sides and then divide by 2. So let me show you how the process works out. I'm going to give you two examples. We have CH4 plus O2 forming CO2 and water, basically your combustion reaction. We balance the carbons first, excuse me, followed by the hydrogens. I'm going to do it the algebraic way though to show you everything, how it pans out. Now, if you look at the balancing that we did before in algebraic form, the amount of carbon is equal to x. The amount of hydrogen is equal to y in the hydrocarbon. So x has to be equal to 1, y has to be equal to 4. We know that for the balancing equation here, 2x plus y over 2 oxygens has to equal 2z oxygens on the left side. But notice this, we know that x is 1, so we already know the balancing coefficient of CO2. And since y equals 4, we know that y over 2 has to equal 2. So now we know the balancing coefficient for water. All right, now setting up the equation, 2x plus 1 times y over 2 has to equal 2 times z, okay? And now you input the values. You know that x equals 1, you know that y equals 4. So you're going to find out that 2z equals 2 plus 2, which means that 2z equals 4, which means that z itself equals 2. And the moment this happens, you have found out your three balancing coefficients. X equals 1, y over 2 equals 2, and z equals 2. And so you just input the values into your balanced equation. Now let's do an example, a little bit more complicated, but same logic. We still have a hydrocarbon on the left side. It happens to contain oxygen, but it is a hydrocarbon because of the presence of carbon and hydrogen. Reacting this with O2, so automatically we gotta recognize this as being a combustion, which means that we should be able to predict that the products will be CO2 and water, even if they're not written out in the equation. That's something I want to expect you to know. All right, now let's take a look at the number of carbons, the number of hydrogens in the hydrocarbon. That means that X is going to equal 20, Y is going to equal 38, and Y over 2 will have to be basically 19, right? So we already got two of the balancing coefficients just from that analysis. All right, now the number of oxygens is based on balancing the algebra here, right? So you have 2 times X plus 1 times Y over 2. That's the overall number of oxygens on the right side. On the left side, you have Z oxygens from the first molecule plus 2N. So that addition has to equal the number of oxygens. And by the way, we do know the value of Z because that's the number of oxygens in the original compound. That's equal to 11. All right, but now setting up the equation, we plug in everything we know. We know the value of Z, we know the value of X, and we know the value of Y. So we literally just input those values the way they are. And so we have 2 times 20 plus 38 over 2, which is the same thing as 40 plus 19. And that's equal to 59. Subtract 11 from both sides, and you'll find out that 2n equals 48. Divide both sides by 2, and you find out that n equals 24. And those are your balancing coefficients that you will have to input into the equation. So X will have to be 20 in front of CO2. The water will have to be 19, as far as its balancing coefficient, and the value in front of O2 will have to be 24. And this process, which seems kind of convoluted, but the process is actually pretty straightforward, though, in the sense that you just plug in the numbers and just solve for the unknown. Now, whether you decide to use the algebra or just do this by inspection, the only thing I want to highlight is that the process I has depicted here is a process that you're going to do regardless. If you do this by inspection, you're going to do this. You'll do it in your mind, but you will do it. You will add up to find out how many oxygens you have on the right side of the equation. You will subtract from that the amount of oxygen in your molecule, and then you'll basically divide it by 2 to find out the value in front of O2. And that's exactly what we just did right here. You might just do it in your mind. The cool thing about it is that right here I'm showing you, like, this took about maybe 5 or 6 steps to carry out. And yet, if you get really good at solving this by inspection, you might do this in a matter of seconds without even thinking about it. But I just want to highlight that this is what you're doing in your mind. And that's kind of cool to think about, that all that's happening just in your head. All right, so in the next video, I'm going to talk to you about single displacement reactions. I'll separate them because they're slightly different from each other and require a little bit more explanation.